All right, folks, let's do number 30. A ball swings in a vertical circle at the end of a rope at 1.50 meters long when the ball is 36.9 degrees past the lowest point on its way up. I wish they drew a picture there, but anyway. Its total acceleration is going to be this component at that instant. Sketch a diagram showing, well, at least you're going to have to sketch it. Well, you're definitely going to have to sketch it regardless. Sketch a vector diagram showing the components of its acceleration. So a ball swings in a vertical circle at the end of a rope. When the ball is, this is going to be, when the ball is 36.9 degrees past the lowest point. I don't know what that means, past the lowest point. Normally, I would draw it in whatever direction I feel like, but they do give the I-hats and J-hat components, so I can't really do that. So I might have to look at the, let me see, when the ball is 36.9 meters past the lowest point. So it could go in this direction, or it could go in the, well, let's draw a circle either way. So it says 36.9 degrees past the lowest point. And on its way up, its total acceleration, what the? On its way up, I just looked this up, folks. All right. I did actually look at the solution manual for the first time. Not joking. So this is going to be the angle that they're going to want. So or that they're going to that they ask for. So this angle is going to be 36.9 degrees. And this object, so this is going to be the angle. This object is going to be right here. And this object is going to be some component x and y. We don't know where that is. So let's just say that this is going to be the x-axis and the y-axis. Not that we're going to need it, but you know, I'm just doing a sketch here. And they say that the component for the acceleration is going to be negative 22 in the I-hat direction and 20.2 in the J-hat direction. So let's just say, for the sake of just, you know, drawing it, let's just say that this acceleration is going to be somewhere in here. And that acceleration is going to have the component at negative 22.5 meters per second square in the I-hat direction. And notice that this is going to be this component right here. This is going to be the component for the I-hats and the J-hats. Plus 20.2 meters per second square in the J-hat direction. And I guess that's part A right there. So I guess what we're doing in this problem is that we're going to define the angle to be 0. So let's say that this is going to be a circle, and that you're going to have some component of the A radio right here. But that magnitude of the component is not necessarily in the direction of the A radio. So it's just going to be some arbitrary point. And I don't know if this helps. Oh, actually, it might help. Or might not. I don't really know. I don't know how to do this problem at the top of my head, but I'll figure it out. So this is going to be this is going to be the velocity vector of the final position. So part A, we already sketched the diagram showing a vector diagram showing the components of the acceleration. Now we're going to be asked for part B. Determine the magnitude of its radial acceleration. How do you determine that? How do you determine this magnitude to get to that component? Notice that this is a bit involved for this problem. Yeah, and I mean, is there some geometry that we have to work out? I don't really know. But what we do know is that we do know that this has a magnitude. If we are given the components, that means that we have the magnitude of this. But given the magnitude of this doesn't really give us the angle or that component. However, we do know that the angle here, they do give us the angle. So we could definitely work out the direction between this point and the A radial. We could definitely work that out. We can definitely find that and take the dot product or whatever and get that angle and get the components or whatever it is that we need to do. So I'm going to do a bit of logic here. I'm going to not pause this video. I'm going to spend like a minute thinking about this. I'm going to spend my time thinking about this. And I'm going to think a bit about what is it that I want? What is it that I want to accomplish? I want to get the A radial. So, and as the thing says that this ball swings in a vertical circle at the end of a rope of 1.5 meters long, is going to be let's say that the radius is going to be 1.5 meters long. So notice that I am taking my time on this, guys, because ultimately what I want to know is radial acceleration. So how do I do that? I know there's a formula in the read and everything like that, but and I know I did solve this before. I just don't keep track of anything. So A radial, so we are given the magnitude. So I guess we could find that point, but we have to be a little careful in the trigonometry. So I'm gonna take 360 degrees, or I'm gonna take 270 plus that degree to get the point of x. Or let's see. I guess we could get. Oh, I guess we can technically get this direction. Yeah, let's do that. So what is the A radial? What is the direction of A radial? The direction of A radial is going to be. I'm going to write this. Because remember, we only care about the direction. We don't really care about which point that is. So I'm going to do this. I already have an idea. And no, folks, it's not the same thing as this component. I'm talking about this component, the horizontal. So it's a little tricky on this problem. So this problem, I'm going to take this 30. However you guys want to solve it, I don't really care. I'm going to take cosine of 90 degrees minus theta. That's going to be the I hat direction plus sine, and then make sure you put a plus, 90 degrees minus theta in the j hat direction. Now I'm going to change. Now I'm going to worry about the signs. Now I'm going to take the signs and I'm going to put a negative here for x, and I'm going to do the same thing for y. Oh no, or actually I'm going to keep that as positive. So already this is going to get this component right here. And it doesn't really matter what the magnitude is for that direction. This is just some arbitrary vector that I just made here. So that vector is going to be here somewhere. It's going to point in this direction. It's not the actual A radial, but it's going to be that direction. And I'm going to take that, and I'm going to take the dot product. Ooh, see what I'm saying, folks? I'm going to take the dot product between A. So I'm going to say that this is going to be some vector, V, maybe not. Let's call it, let's call it R for now. So this is going to be the R vector, not the position vector, even though they're usually the same. But I'm going to define this to be R, and I'm going to take R, the unit vector of that vector, and I'm going to take the dot product. And if you know your dot product, the angle between that is going to be this radial component. So once you have that, you have that angle. So now we already have that. So let's dot it this. So let's take the component that we're given, 22.5 meters per second square, but that negative goes away, multiplied by cosine of 90 degrees minus theta, and I'm going to add that to plus 20.2 meters per second square, sine of 90 degrees minus theta. There might be an easier way to do this problem. This is the way I'm figuring it out. So once you take the dot product, folks, what we're going to be doing is we're going to multiply by the magnitude of 1, because that's what this is. That's what this unit vector is. And then we're going to multiply by the magnitude of A, of the magnitude of A. So get that. Let's find out what those values are. So, so I'm going to store this into theta. And remember, folks, that this is going to be cos of theta is going to be equal, but that theta is going to be, oh, that's a different theta. I'm going to call that theta naught. Yeah. This is theta right here. This is going to be different. So that's going to be the angle that we're going to be looking for. Once we get that angle, all we have to do is take that magnitude and we take the cos inverse. Let's see what we. All right, folks. So once you get this value and take the cos inverse, theta naught is going to be 11.18 degrees. So that means that we're going to take the magnitude of A. We're going to take cosine of 11.8 degrees, whatever that is. And that's going to be the A radial. That's going to give us the A radial that that it's asking for. So the A radial is going to be 29.66 meters per second square. All right, so that was part B. Notice that it was a bit involved. And I just figured out that it's really just a dot product. You don't really have to. I kind of like got the angle and took the magnitude, but you don't really have to do that. Just take the dot product and you're done. Anyways, I did look at the solution manual and they do it the same way, actually. I'm actually see folks, when you do applied mathematics and you know your stuff, you're gonna arrive to the same solution without independently from the book. All right, so determine the speed of the velocity of the ball. Notice that in that equation we didn't really care about the, we didn't worry about the speed, but now we are. So this one is going to be v squared over r. So that means that A is going to be the square root of the velocity is going to be the root of AR. So so let's see if I store this. I got my value, but I'm going to find it again. So A is going to be 29.66x. The radius is going to be 1.5. The square root of AR, that's going to be, the speed is going to be 6.67 meters per second. Hey, we're done. All right.